Okay, this is a YouTube for last quiz. I'll go over each question, starting with question 1. A spring-loaded projectile launcher has adjustable launch speed from 5 meters to 15 meters per second and adjustable launch angle from 0 to 90 degrees. 0 degrees corresponds to vertical, 90 degrees to, 0 degrees corresponds to horizontal, 90 degrees corresponds to vertical. The projectile is launched from the floor and returns to the floor. A. What combination of launch speed and angle give the largest flight time, and what is this flight time? Alright, so we would use kinematic equation number 1, which is Vy equals Vy naught plus 2Ay times t. I would set Vy equal to minus Vy naught in order to get the flight time. And Vy naught is V naught sine theta because this is projectile motion. And so that would give us a flight time of 2 V naught sine theta over g. Clearly, to maximize this, we want to pick V naught as large as possible, and we want to make sine theta as large as possible. So V naught we can make 15 meters per second, theta we can make 90, and in that case we would have 2 times 15 meters per second divided by 10 meters per second, using a g of 10 meters per second, and the flight time, maximum flight time, would be 3 seconds. B. What combination of launch speed and angle give the maximum projectile height, and what is this max height? So for that, I would use kinematic equation number 3 and put Vy equal to 0 and Vy naught equal to V naught sine theta, and Ay would then be equal to minus g. Then we could solve that for delta y, and we would get V naught sine theta, the quantity squared, over 2g. And so we want to maximize what's inside the parentheses here to get the largest height, upward displacement here, delta y. So clearly we want to make sine theta 1, theta is equal to 90 degrees, and V naught should be chosen to be 15 meters per second. And in that case, we'd get 15 meters per second squared divided by the quantity of 2 times 10 meters per second. There's a typo there. That should be a second squared. 11.25 meters is the max displacement. C. What combination of launch speed and angle give the maximum range? What is this max range? So the flight time is 2V naught sine theta over g. We got that up here. And then the range is then simply equal to the x velocity, which is constant the whole time the projectile is in the air, times the flight time. And so that gives 2V naught squared cos theta sine theta over g. But using the double angle formula, that becomes V naught squared sine 2 theta over g. So to maximize this quantity, again, we want sine 2 theta to be 1, which means 2 theta, it needs to be 90, which means theta needs to be 45 degrees. And then we'll pick V naught to be 15 meters per second. And that's the largest selection we can make. And so ours would then be 15 meters per second, the quantity squared, divided by 10 meters per second squared, since sine of 2 theta is equal to 1, and that comes out to be 22.5 meters. D. Find 2 combinations of launch speed and angle that give a projectile range of 15 meters. Well, there are infinitely many combinations. So what I did, and you probably did something different, is I took V naught to be the maximum 15 meters per second, and then in that case R is equal to V naught squared sine 2 theta over g. That's a general formula. And now I'm going to solve for sine 2 theta. Since I've chosen my V naught and we're targeting a certain R, then I simply have sine 2 theta equals, with these numbers, 2/3. And 2 theta is equal to the inverse sine of 2/3, which is 41.8, but it also could be 140 minus 41.8, 138.2. And so my 2 solutions are 15 meters per second projected at 20.9 degrees, or 15 meters per second projected at 69.1 degrees. Both of those would give the same 15-meter range. Okay, question 2. There were some extra words here, and it turned out there was a typo that I had. I apologize for that. But essentially, you have this blade which accelerates from rest, and in one rev propels M around so that it gets back to the initial angular position and very quickly stops. M, the electromagnet holding M to the blade, disengages, and then M flies off. And so the table is 1.5 meters off the floor, and what we want to do is we want to hit a target that is straight ahead here, 1.5 meters from the base of the table. So I ask you to find a combination of blade radius and blade omega at the instant of launch that will cause them to hit the target. So I'm assuming that we can pick R from somewhere starting at 10 centimeters going up to 20 centimeters. So I'm going to take an R equal to 20 centimeters, 0.2 meters, and I know that V naught x is R times omega, and I also know that that initial x velocity has to be 5 meters divided by the flight time, and it's going to be constant the whole time it's in the air. So I can figure out the flight time by using kinematic equation number 2, which the simplified form is 1/2 GTF squared equals h, h being the height of the table. I can solve that for the flight time, and it's the square root of 2 times the height of the table divided by the acceleration of gravity, 0.55 seconds. And that means that R times omega is equal to 5 meters divided by 0.55, which is 9.1 meters per second to 2 sig figs. And then omega is, turning things around, is V naught x over R, so it's 9.1 meters per second over 0.2 meters, which is 45.5 radians per second. Okay, so the next part B says, assuming constant alpha in a single revolution of B from a stationary position to the final firing position, find alpha if the time taken for B to rotate once is, well, okay, so it's 0.276, not 0.250. My apologies there. It has to be because, well, if you use the best equation to use for this one would be equation number 3. Because we know everything except for alpha, and if you solve for alpha, you get 165 rads per second squared. On the other hand, if you knew what the t was, if I'd given you the correct t, you could have solved for alpha from this equation, since omega naught is 0. Alpha is then the final angular velocity divided by the time, which is 45.5 rads per second from part A divided by 0.276, which is the same acceleration number. Or you also could have found it from kinematic equation. This would be 2, the analog, of course. These are, when I say 1, 2, or 3, or whatever, I'm talking about the analogous rotational equation. Okay, so however you did it here, as long as you followed one of these 3 paths, whatever, using a quarter of a second, if you did it this way or that way, you got credit. If you did it this way, that would have worked too. So the last question was find the tangential and radial acceleration of m at the instant of launch. Well, the formula for the tangential acceleration is r times alpha. 0.2 meters times 165 rads per second squared. We just found alpha here, and again, I gave you credit if you, whatever alpha you derived using this 0.25, I gave you credit for that. That turns out with my numbers to be 33 meters per second, and then the radial acceleration is r omega squared, 0.2 times 45.5 rads per second. The quantity squared, 414.1 meters per second. The radial acceleration being much the larger of the two, over a factor of 10 higher.